All right, so what we got going on is this week we're going to be doing regular assignments. Next week we have the semester exams, so we're going to review for those Monday and Tuesday, and then you'll start to take them Wednesday, Thursday, and Friday, depending on what class it is. Those are all going to be half days for y'all. So we got regular assignments to do today. Thursday, I will not be here. I will have a sub Thursday. So make sure that whenever you'll probably have a quiz to take in Sapling on Thursday. So whenever you get done with the quiz, find something quietly to do. Don't be talking to people or messing around. Sit in your assigned seats. I'll have seating charts for the sub and instructions on what y'all are supposed to be doing and not doing. But it should be relatively easy. Keep these study sheets that I'm about to hand out because they will help you. Today's assignment and the quiz. I think I have a separate study sheet for the assignment for Wednesday and Thursday, but I'll give that to y'all on Wednesday. So what we're going over today is the shape of molecules. The different shapes of molecules. I think there's two there. And that's what this VSEPR is. I say VSEPR. There's no V or no E in between the V and S, but you can see it. It says VSEPR, right?
Yeah.
VSEPR. Do you want to make it a word? It's not a word, but it looks like it says VSEPR. VSEPR.
Kind of fun trying to say it without the
Yeah, VSEPR. So that's what I go with. That's what I want y'all to think about. And basically, this is the system for which we kind of figure out what the shape of these molecules are, because the shape of molecules are very, very important. Y'all kind of learned this through biology. We talked about the shapes of different molecules and how you have receptors that accept those shapes. It works the same way in chemistry. The shape of your molecule is going to help determine how it combines with other elements, whether it can or cannot combine with other elements, and in general, what kind of properties it has. And so shape is very important, and it's great if we have a way that we can determine the shape of a molecule without having to stick it under a super high-powered microscope and actually see it with our eyes. In the same way, there's all sorts of things with math and with history and all sorts. I don't know. I can't think of a good example right now. It's early. But things that we need to be able to work out really quickly without actually having to see with our own eyes. We need to be able to do the work. And so that's what VSEPR is. If I just make up a molecule, I can figure out what that shape is going to be without having to go look it up somewhere or actually see it with my own two eyes. And so what they have listed underneath VSEPR here are the different shapes. We have linear. What's linear going to be?
a line.
Just a line. Linear is a line. Bent is going to be a bent line. Trigonal, planar. What does trigonal planar sound like? It might.
Triangle.
It's going to be like a triangle. And planar means like flat. So it's going to be like a flat triangle. Trigonal pyramidal is going to be like what shape?
A pyramid.
A pyramid. But if you think about it, the pyramids that we think about, like the Egyptian pyramids, how many sides do those have?
4. 9.
4. What's a trigonal pyramid sides going to be?
3.
3-sided pyramid. Yeah. So instead of a 4-sided pyramid, it's a 3-sided pyramid, which is basically the same. If you think about it, the pyramids in Egypt, what's the bottom shape of the bottom part? It's a square. This is going to have triangles everywhere. Instead of a square at the bottom, it's going to have 3 sides and a triangular bottom, which kind of makes a little bit more sense. And then at the end, tetrahedral. What does tetra stand for? 4. So this is going to be a 4-sided molecule, or a molecule that has 4 kind of equal appendages in a way. So learning objectives, we're going to learn the VSEPR theory and figure out how to make the shapes. VSEPR theory is a theory used to determine the shapes of molecules by taking into account the number of valence shell electron pairs that are repelling one another. It literally stands for V is for valence, shell, electron, pair, repulsion. And electrons are what charge?
A negative.
A negative. What are negatives going to do to other negatives? They're going to repulse. They're going to go apart from each other. Where negatives and positives are attracted, double negatives or double positives, they want to move away from each other. So that's what that repulsion is. So if we look at where the electrons are at, that can tell us how far they want to move apart and what kind of shape we're going to have. So valence shell electron pairs are repulsed by each other because they have like negative charges. Electron groups around the central atom keep as far away from each other as possible, and that kind of helps determine the shape. So molecules take on different shapes to keep valence electron groups as far away from each other as possible. Was that a video? It was just, yes, it is a video. So when I add in another shape here, I'm linear, right? If I add in one more group of electrons, video's not cooperating. So when I add in one, I'm linear. If I add in another one, I go to trigonal. If I add in a fourth one, I go to tetrahedral. Well, no, I guess that would be trigonal pyramidal, and then tetrahedral will be a little different. So you'll see these in a second, kind of all together. So bond angle, we can actually measure the bond angle. Bond angle is the measurement of the angles between bonds in a molecule. Bond angles can be predicted from the number and type of electron groups in the central atom. So we look and see how many bonds there are, how many extra electrons you have, and that can kind of tell you the angle. So we got a couple terms here. Lone pairs is a pair of electrons that does not participate in bonding. So in the last section, we call these non-bonding pairs. Lone pairs also works out. Notice it's right in the name. There's two of them. So if there's two little electrons, they're not going to bond to anything else. Only your single electrons end up bonding. Shared pairs are going to be your bonding electrons. They're shared in between two atoms, which by definition makes them a bond. So shared pairs are the valence electrons that are shared in covalent bonds, also called bonding pairs. Lone pairs require slightly more space than shared pairs. Molecules with lone pairs present on the central atom have slightly different shapes than those without. So their example here, this is what you're going to use the most on your assignment today. Everybody sees this chart on there. This shows you the different shapes here. So we go from linear to trigonal planar to bent to tetrahedral, trigonal pyramidal, and then another kind of bent where I have two electrons instead of one. So here they have two, and there they have one. So although more electrons are shared in double and triple bonds than in single bonds, the electrons still occupy only one region around the central atom. Do not distinguish between single and multiple bonds when determining molecular shape. So basically, doesn't matter whether it's a single, double, or triple, it's still going to have the same shape. You're just looking for bonding groups around the edge. Each bond, no matter the type, should be counted as one electron group composed of shared pairs. So linear. Now we're going through the actual shapes. Linear, molecules with two groups of shared electrons and no lone pairs. So look, there's no extra electrons. There's no extra dots. I just have two bonds there. So two shared pairs of electrons and no lone pairs around the central atom. The bond angle is 180 degrees, which basically makes it flat. So it's a linear molecular shape. They're going to give us an example. This one's actually a little bit complicated. This is dimethyl zinc. So I have zinc in the middle. I have carbon on either side. And I have some hydrogens out here to the end. But the most important thing is, how many bonds do I have coming off of my zinc? Just two. And these actually in real life might be like double bonds. I think they would be double bonds here. No, I guess they wouldn't be. I'll have to look that up. But anyways, you have two bonds here. Are there any extra electrons around the outside? No, they don't show you any other dots. And so there's nothing that's going to push this down or up. It's just going to stay nice and flat. And so your molecule looks like this, which is a linear molecule. It's not bent. It's not trigonal. It's not tetrahedral. It's just a straight molecule. Does everybody kind of see that? So if I just have two electron shared pairs around that central atom, the central atom is the most important one. If I just have two there and no extra electrons, it's going to be linear. Now, same thing if they're double bonds. now they show you double bonds with carbon. I have 2 sets of double bonds on either side with no extra electrons in the center, so it's not bent in any way. It's just a 180 degrees regular linear molecule. So if you go back to that chart there, you can see for the linear shape, the top line in that chart, total number of electron groups around the central atom was 2. So I have 1 here and 1 here. Total number of shared pairs, which are bonds, I have 2. How many non-bonding pairs do I have? I don't have any around there. And so 2 and 0 are my numbers for shared pairs and non-bonding pairs. And then that gives me a linear molecule. So you just kind of follow the chart, and it should tell you the structure. Now we go to bent. If you look at bent compared to linear, bent is either going to have 3 or 4 electron groups around that central atom. So they're going to show me in a second right here. This SN is the element 10. It has 2 bonds around it, but it also has a non-bonding pair. So this has 3 groups of electrons around it. I have the 2 bonds and then 1 lone pair. And so if I follow on the chart, an element or a molecule that has 3 bonds, with 2 being shared bonds, 1 being non-shared lone pairs, that gives me a bent molecule that has a bond angle of 118 degrees. Does everybody see that? Following along on the chart. So that's going to be your shape here, 118 degrees, because I have 2 bonds and 1 non-bonding pair. What's going to happen here, these electrons in the bond are being pushed away by that non-bonding pair up top. So instead of being flat 180 degrees, now I have a pair up here, and they're repelling the other bonds or the other electrons in these bonds and kind of pushing them down. And so it's going to be close to, but not quite, a perfect triangle here. The only difference is there's not a bond in another element. It's just an extra pair of electrons. So they have another one with bent. Notice we have 2 bonds, but this oxygen has 2 pairs of lone pair electrons, non-bonding electrons. And so that's going to push these 2 bonds down even more. It's going to push them down to a more extreme angle, and you see the angle's a little bit different, 104.5. That's the bottom row down here. So total, I have 4 electron groups around my central atom. 2 of them are in bonds. 2 of them are not in bonds, which gives me a shape of bent and an angle of 104.5. Now we go to trigonal planar. This has 3 bonds around it and no extra electrons because it's going to keep everything nice and flat, which is the planar part, and all the angles are going to be the same, which is the trigonal part. So here we have aluminum in the center with 3 bonds around the outside, and chlorine, each having some extra electrons on the end, but they don't really influence the shape. And so if I look on the chart, I have 3 bonds total, all 3 right here. All 3 of them are actual bonds. None of them are extra pairs around the outside. So that gives me my shape of, actually, maybe I should change this. But anyways, you can see. This doesn't actually tell you the name of the shape. It just shows you the like image of the shape. But this is trigonal planar, and it's 120 degrees. What's 120 degrees times 3? 360. And so we take the full circle and we divide it into 3 equal parts. And so it's 120 for the angle there. Now, if I take that same shape and I add in 1 extra group of electrons, which is about all I can have, now I have a total of 4 electron groups. 3 of them are bonds. 1 of them is a non-bonding pair. That's going to take all my bonds and push them down. And so here you see I take that trigonal planar shape, I tack on some extra electrons on the top, and it takes those same bonds and just pushes them down towards the bottom. And so now my bond angle is 107.3, which you can see on the next to last line here. And then finally, tetrahedral. The difference between tetrahedral and trigonal pyramidal. Trigonal pyramidal, the tri tells me I have 3 bonds, but the pyramid shape tells me that I have 4 total electron groups. For tetrahedral, I'm still going to have 4 electron groups, but it's going to be 4 bonds. So you see the difference between those. Tetrahedral is going to have all 4 of them tied up in bonds. There's not going to be any extra electrons. So like carbon and 4 hydrogens around it is going to look like this. It almost looks like that trigonal pyramidal, but there's actually an atom up top and not just a loose group of electrons. And so for the most part, you're going to use this chart and use your knowledge of how many dots each of these elements should have to figure out what the shape should be. So they have 3 steps for determining molecular shape. Step 1, you got to draw the Lewis dot structure of the molecule, and it's best to start with the central atom. Step 2, count the number of electron groups around that central atom. Step 3, note the number of electron groups that are composed of loose pairs and of bonding pairs. So I said loose pairs, it's lone. Lone pairs or bonding pairs. Determine the shape based on that. You're going to use the chart. So it tells you here, I got the total number of pairs of electrons around the central atom. I have the bonding pairs in that first column, and then the lone pairs in the second column, and then they tell you the angle and the shape. So for example, CH2O. So what are my different elements here? How many dots does carbon have around it?
4.
How many dots does carbon have around it?
4.
4. How many does oxygen have around it?
6.
6. And then how many does hydrogen have?
1.
1. So carbon has 4, oxygen has, and then I have 2 hydrogens. Each of them have 1. Now, which one has the most bonding electrons? The carbon. That's where I'm going to start off with. So I'm going to have carbon in the center. 1, 2, 3, 4. I don't really know where this is going to go from here. I'm guessing I'm going to have a double bond to an oxygen. So I'm going to bring this down here. Have a double bond to this oxygen. 1, 2, 3, 4 here. And then a hydrogen over here. Single bonded. And then a hydrogen over here. Single bonded. So how many bonds do I have around my central atom?
2.
Well, bonding, I guess, regions or groups. There's 3. So I have 1 here, and even though this is double, it's just going to count as 1 kind of region of electrons. So that's going to be 3. So I have 3 bonds and no extra electrons up top. So using the chart, what's the shape going to be? If I have 3 total groups, all 3 of them are bonds and none of them are lone pairs. It should be trigonal planar, yeah. So I should have this kind of shape with 120 degrees and no extra electrons. So let's see if I got that right. So draw the Lewis dot structure. Yes. So now we have the same thing. It's oriented a little differently. But I have 2 hydrogens with single bonds, and then a double bond to the oxygen, and it has a couple extra electrons. What are my number of electron groups? There are 3 of them. All of them are bonding. And so my shape here, it's going to be a little wonky looking because the oxygen is much bigger than the hydrogens. But this is a trigonal planar shape here. And if they ask you about the angles, it'll be 120 degrees. So that's it. I will leave this part up. And if you have any questions, let me know. We can kind of go through them on the board for a couple of the questions if they're difficult. Y'all are the first class to have done this today, so we'll see if that helps you out at all. But I will turn the lights on. For those of y'all at home, this is what I wrote a little bit. I can turn this way. And it should be up in the sign. Y'all see it? Cool. Stop.